factor, that means like it's not difficult to see that like a time that discount term would behave something, it would decay exponentially, right? So it would fade away, and since it fades away, you are, while trying to maximize this overall expectation, you are prioritizing near future as compared to farther future. Right? So, something that we should put here, because it was just on a whiteboard. So pi is a policy. This is a policy. So policy is the law that yields actions based on the current state. So in the policy could be stochastic or deterministic. So when it's deterministic, it's fairly simple. It's just a function of state. When it's stochastic, it's a PDF condition of the state. So, like in this case, A takes S. In this case, A. Now it's random variable is sample from Y. So, now one important thing, and you will find this, for example, in popular frameworks such as in Baselines 3, for example, is that the standard terminology utilizes what's called an observation. So here's the thing. Imagine like there's the environment, and so this environment has its state. In that state, it evolves according to the state transition law, and state, like, normally it's a kind of intrinsic property of the environment. So when we deal, let's say, with a mechanical or electromechanical system such as a robot, to actually, like describe dynamics of the robot, it might mean, packing quite a lot of stuff into that state with all the possible, turn angles. This is some sophisticated manipulator, and maybe it's like even on a car or something, or even just let's say, dog robot, quadrupedal robot that might have some 26 degrees of freedom or something like that. And then think about this. You are eventually, when you are trying to maximize this statistic over here, well, evidently it means finding optimal policy. And you see optimal policy, right? It takes the states as an argument. What that means in practical terms is that state gotta be somehow measured. I mean, especially if we're talking about physical applications. If some torque or force, maybe like a group of robots, contact force, if that constitutes a state component, and your policy is so designed that it needs that, then it would be a task, a challenging task for you, to install, to get proper sensors, install, calibrate, and so on and so forth. So, in order to simplify this story, there is another term that's called observation. So, observation is denoted by by a terrible letter O, that actually, generally speaking, it's also sampled from, let me check the notation real quick in order to stay consistent. Yeah. So let's say it's the page. So it's also sampled from a separate PDF, normally conditioned just on the state. Sometimes also on the action, but it's a more complicated situation. So what could that be? One immediate example is when you got the state. It could be a fairly large vector consisting of all all the key physical variables constituting macroscopically speaking physical state. And you just measure just a part of it. So, for example, you don't directly have access to like torques, forces, stuff like that, because force torque sensors, they are expensive and sometimes maybe not particularly reliable. And you've got something simpler, something cheaper and more sustainable. I don't know, encoders. So you just measure, for example, you've got some odometry in the end. You get the revolution speed and something. So partial state is an example of observation. Another example is, as I brought up yesterday, what if so let's say you are balancing a cart pole or just a pendulum. Now imagine this kind of game. So you've got a rod, and then there's a cart, and on the cart there's the pole, right? And you as human, you can press two buttons. Cart full left, cart full right. Would you be able to upswing and hold? I mean, if the cart pole is not too peculiar, if it's like balanced, and would you be able to do that? We had some exhibitions in Germany with such a test stand to demonstrate control theory and stuff. We had a stand, we let kids play with it, and they managed to do that. But you see, like they're just pressing the buttons and watching the cart pole. They're not touching it. a classical controller for a car pole would probably require at least two things. It's the turning angle. Maybe also if you want like drive the car to some target position, that position, and probably also angular velocity. All of that, as soon as we're talking about classical control, all of that would be require measurement of this quantities, right? But if you don't have the sensors, you just look at it, and that's an example of application where classical control theory would struggle, unless, of course, you can do some classical computer vision, and just kind of get that angle and then estimate the angular velocity. Of course, yeah. But in reinforcement learning, you can go without classical computer vision. You just take the policy, which is modeled by a neural network, and put a convolutional layer on top, for example, or a couple, whatever. Just say a CNN on top. And you can train it. You can train it to upswing and balance the car. What did I just describe? I described a non-trivial situation where an observation, what is actually perceived by the agent, right, by the policy, does not coincide with the state. Like you physically describe the car pole via, position of the car, right, turning angle, and angular velocity, right? Maybe also this horizontal velocity, translational velocity. That's how you would describe physically that environment. But it's just so designed that you don't have the sensor data, or you only got a camera, and the camera is looking at the car. So, but at least in our theoretical derivations, we will mostly we will just assume that, that they be identical. Because, introducing an observation makes things way more complicated from the formal standpoint. All right. So, I guess that's more or less, yeah, so we want this to be maximized with respect to policy. All right. Now, I want to get to the tabular. We'll start with the tabular. Before that, are there any remaining questions on the context? About the context? All right. So, now, get this. Let me write down, just copy. So, we once again start with the problem setting.
Can you rotate the...
Oh, yes. So, introduction to tabular reinforcement. So, here's the problem that we start with. I will also assume here deterministic policy and identity between the state and observation. So why am I insisting on deterministic policy? It's convenient, it's easier to derive, and most of the time deterministic or greedy policy maybe, well, not like you see, there might be some, absolute probability for exploration, stuff like that. But before we get into these fine details, okay, what we want to do is we want to derive the most essential, basic recipe to do temporal reinforcement. And for that sake, we will concentrate on deterministic policy. So our policy will be like that. So the environment is written there in the specification of the expectation value. And there is no observation, just pure state. And now, when you just look at this thing, there's already something to think about, right? How to solve this? This how? Well, if you come from the data science perspective, if you look at it from the data science perspective, well, you see like, okay, maximize, it's an optimization problem, and I know how to solve optimization problems. I just take some fancy gradient like algorithm, atom, whatever. And you would be right. That's exactly what policy gradient does. But it just so happens that it's fairly tricky to actually compute this, to actually come up with computation tractable expression of the gradients. You cannot put this in code. You can't just take the gradient of that and put that in the code. So that's a different story. It's a different story. And it's a little sophisticated. But another perspective on this problem is from the standpoint of the good old dynamic programming. Who of you have heard of dynamic programming? Just this term. So, dynamic programs, like optimization problems, traditionally have been called like linear programming, for example, quadratic programming, nonlinear programming, mixed integer programming, whatever. Dynamic programming is also programming. It's about an optimization problem. But in this case, why it's called dynamic? Dynamic is called because we are considering a Markov chain that exists dynamic in time. When you hear dynamics, it should immediately get association that there must be time. There must be some variable that represents time, or steps, whatever, as soon as we're talking about dynamics. And dynamic programming, although not like directly mentioned, for example, in NASA reports about Apollo missions, not so evidently, but it was in fact used for flight trajectory. I'm not an expert in that. I just skimmed through NASA reports out of curiosity. The formulas there, they were like, yeah, it was dynamic program. So they used it for flights and also for the rover, something like that. So, and that was like long before neural networks even got popular. So the roots of dynamic programming, they are like something like late 50s, early 60s. Thanks to Richard Bellman and forgot the name Blackwell. So they derived the fundamental building blocks of dynamic programming. Although I wrote in I was writing like a historical overview of dynamic programming in my second dissertation, and I got a comment by the reviewers. Maybe I'll post that later on the Telegram chat. That actually Bellman was not the first. There was another German guy. And by the way, Richard Bellman was, if I'm not mistaken, a student of Solomon Levshin's, one of the prominent mathematicians of the Soviet Union. And by the way, he didn't have hands. He lost his hands when he was 30. He was engineer something that he decided to be a mathematician and turned genius mathematician. Okay, so what I will try to do is just this. I will unwrap this objective and try to solve it recursively. You see a sum, especially if there were like infinity, there, it's kind of asking, to try something like that. Like can we solve recursively? So in order to do that, I will split the sum over here, okay, into two. Now, in order not to get lost in this, what would be then what's called like a head part of the problem and a tail part, and I split the problem and all that, I will introduce a term called value or value function. So it's basically just the objective. So value denoted B notice I'm using small letter. If I recall correctly, the subpart also used small letter for that. Again, in order to avoid confusion with random variables. So now, if you look carefully here, if you look carefully at this sum, what does, or this statistic overall, what does this statistic depend on? Can you tell me? Well, one evident answer, just this statistic, it depends on what? Say it. Policy, of course. But anything else?
S0.
Yeah, starting state. So that's why. So value is just it's just an alias for that objective. Okay, we can just straight up copy. Now, in order to be consistent, especially regarding this initial state, let's just write as 0 equals small as 0 or as not. Okay, that's one thing. So there normally goes as argument of the function, of the value function. Okay? Now, this cumbersome description over here, as I told you, is sometimes like shortened into just P, and then of course, well, so here's the thing. Normally, so I prefer to stay clean with notation. So as soon as we are talking about deterministic policies, let's not try to put this as a placeholder for some degenerate ETF or whatever. If you want, you can leave it there. Okay, it's up to you. But maybe it is just fine to write something like that. Okay, you fine with it? All right. So, and now of course, that's a decision variable. It must be put somewhere in the specification of the value, excuse me. So I put this as a superscript. Now, I will mostly follow the convention that subscripts correspond to something like literally time step, iteration index, episode index, okay, you know, bit trickier, even on that whiteboard, it's not following that convention precisely, but anyway, I will try to follow the rule that in the superscript, I put something that is not timeline, that is not related to time steps. So for example, if I am talking about the value of the policy pi, I put pi on superscript. Okay? Because afterwards, for example, when we introduce value iteration, we'll have iteration indices. The value. Okay? That's why. And I want to leave that as a subscript. Now don't underestimate. I'm telling you that cleanness of notation is like 40% of you succeeding not just with math, with the code also. Just believe me. All right. So as promised, let's just split. So now we just split. So B pi as not would equal R as not pi as not plus same thing. Except that here we need to do some refinements. Of course, well, first of all, we are starting now at, so what I did, I just pulled out one term. Okay. Now we're starting at step one. This is the second step. Well, now of course, S1 is so like this condition over here, that was clear. Just saying, starting state is definitely small s naught. Okay, definitely. Next one, the state S1, it's not definite anymore. It's random. So, what would you do there? How would you write the condition? Anyone give me a hint? What should I write here for condition?
It should be something from distribution of states.
State transitions.
Yeah. State transition.
Like this?
Yeah.
Do you want to specify anything else?
From current space under the condition of previous state space and
No, don't go state. State space is the whole space. State.
state. Yes, in the current condition, the previous one, and take an action.
What action?
Take an action. Well,
Taken action.
take an action.
What is the action? Name it.
It's opposite from previous one.
Yeah, what is that? Just name it.
Yes.
Yes. Zero.
So, that now makes sense, and that also wait a sec. Okay. So we split. Yeah. Now I want to relate this to the optimal value. So what is the optimal value? Just maximize with respect to, policy. And I will denote that B star. Well, evidently, that value should not be less than any other value, any other policy. What's that? This is policy space. Can we type something like that? Get the equivalence, right? If that thing don't exist, then let me know. I'll fix that. Anyone got like a lead at hand? Just type and check. Okay, so that would mean that optimal value would in particular be bigger than any term of this form for any policy, right? So, and after the break, we will derive some interesting properties of the optimal value. Now, as I promised, let me check the depth. Okay?